Hello everyone and welcome back to the Kokkos Lectures. Today we're going to talk about hierarchical parallelism in our module 4. Before we go there, as always, all our resources, GitHub repositories, and then obviously our wiki for the Kokkos Lectures. That's where you find all the slides and recording and Q&A for the lectures. I didn't add the link yet for the current slides, but the slides are already in the Kokkos Tutorials Lecture Series folder. So if you just pull again, you get these slides. Also, our API reference on the main Kokkos wiki. If you want to look anything up, in more detail of what we are talking about today, you can find that there. And then, as always, please feel free to join our Kokkos Team Slack channel to get all your questions answered. So we are in module 4. Today we talked before about, just simple stuff like parallel dispatch. We talked about how to build things in module 1. We'll talk about views and spaces. How to get your data allocations going and how to manage heterogeneous memory spaces, as well as how to execute in different execution spaces. And then last week we talked a lot about more advanced data structures, things like how to get subviews, how to handle scatter contribute patterns. We also talked about tightly nested loops with the MD range policy. And let's look at that in a bit more detail. We started last week with the MD range policy. We talked about these tightly nested loops, which is kind of similar to what the OpenMP collapse clause does, and how we can use that for both parallel 4 and parallel reductions of 2 to 6-dimensional loops. We talked about the tiling strategy over the iteration space, so that MD range policy actually does tiling by default, and we're going to see that in a moment when I walk through the exercise for MD range policy, and that you can control these iteration patterns at compile time. We then talked about subviews, how you can take slices of views and how that is very similar to what you can do in MATLAB and Fortran or in Python. We talked about how you should prefer the use of auto for the return type, because it's actually pretty hard to figure out what is coming back from subview. But we also showed you, we talked a bit about ways how to work around that, and there's a couple more answers in the Q&A for that module. When we talked about unmanaged views, which allow you to interoperate with externally allocated arrays, so essentially you can create an unmanaged view just from a raw pointer in the dimensions. It's unmanaged because it doesn't do reference counting, so there's no memory management happening underneath. We are not deallocating a destruction or something like that. And you are responsible as the user for ensuring that all the dimensions are matching what you actually had done, with a raw pointer, that the memory space is correct, that the layout is correct, etc. And if those things don't match, you get kind of unexpected answers, right? So in the best or worst case, depending on how you feel, you just get the wrong elements when you, access it. In the worst case, you just crash. Like either you got, have out of bounds access, or you give like a host space view to deep copy and it thinks it's a host space thing. And it actually was allocated with like CUDA malloc, then you will crash with the segmentation fault. We also talked a lot about atomic operations, how we are available, on host and device, that we support like generic atomics on pretty much, any kind of data types, that you can actually do things like atomic add and atomic multiply as long as the underlying data structures have, or the object types have the associated operators implemented, like plus equal. We talked about how you can make a whole view atomic by using the memory trait atomic, and that allows you to essentially have every single plus equal or assign or whatever be atomic on the view. We also talked about scatter view and how that helps with the scatter add, or generally scatter contribute parallel patterns, how it allows you to switch automatically between atomic operations and data duplication, depending on whether you are on a low thread count architecture or high thread count architecture. And then we talked about dual views, which allow you to manage data synchronization between host and device, and which help you in codes which do not have a holistic view of your entire data flow, which in particular is important when you start porting codes incrementally. And we have an exercise for that as well, which shows that kind of scenario. Okay, so before we come to today's topics, I'm gonna switch over and walk through the exercises again. Let me do that. I'll go over here, just 1 second. I think it's correct. Okay, so I am in the Kokkos tutorials repo, and as always, you know, this is checked out in the main Kokkos directory in my home directory, and the you know, the pure Kokkos, as of a GitHub clone of Kokkos, is just on the same level. So let's go to the exercises. We started with MD range, so we'll go to the MD range exercise. Let's go to begin here and look what needs to be done. As always, we grab for the all caps exercise clauses to find what needs to be done. And what we need to do here is we need to just replace the initialization calls again with parallel force. The first two will just be normal parallel force. This is something we actually did back in exercise 1. So we'll just do that for now. Init y, we give it a name to, you know, just as a force of habit in order to get the kind of, you know, profiling information out of it, which we will discuss in a later module, how to do that. Copy this guy, copy it here. One thing, we need to change the loop count because it's not n, it's m. So that's the first 2 loops. Now, I'll start with the same one here, but instead of using just the m, right, we now need to use the Kokkos MD range policy. Actually, let me do that in a, let me just create that thing up front. MD range policy. There is a required argument which sets the rank of the thing. So we'll start just simple, you know, with a Kokkos rank 2. And then we give the constructor initializer lists for the start and the end point. Okay. Now we can use the policy here. But we have to change the signature of our thing to do the correct indexing. And what we need to make sure here is that these things match up, right? So we have the outer loop here, n, the inner loop, m. We'll did that here too, the n and m. And the n was for j, and the m was for I. So we have that matching up, which means we can close this here, can move that additional brace, and we can close the whole thing. So one thing I'm going to do is, because I want to show you a couple of things like the impact of the tiling, I'm going to add a timer here. So Kokkos has built-in timer facilities, which are a little bit easier to use than, say, the chrono package. One thing we need to do in order to get proper times, we need to fence here so that asynchronous dispatch of parallel 4 is done by the time we actually record the time. I think I'm using a timer further below, so I need to have non-conflicting names. So I just get the seconds, and what I'm going to print here is I'm just going to print out the milliseconds. I know that it's roughly going to be in the millisecond regime. So what I'm going to do is I'm going to print time 1 times 1000. Okay, let's see if there was anything else which needed doing. Nope. That's it. So let's compile this thing, and let's compile it for the CUDA. See if anybody else is busy on this machine. Hopefully not. What's happening? Okay, good. Just me. So let's run this thing and do a reasonably large problem. So this is like about 500 megabytes. And what you see here is we have this time here, and it's 4 milliseconds. Okay. So what I said before is that in the lecture that MD range policy is not really good in determining tiling sizes automatically. So the first thing we're going to try is we're just going to do the tiling a bit better. In particular, in this case, right, we do not really have any data reuse, right? So tiling doesn't actually help you. So there's no kind of locality information or locality access which can be improved. So what we're going to do is we're going to do a tile size here of, say, 64 times 4. So we do more along the J direction, because the matrix in this case, since I compile for CUDA, is layout left. And so we want the contiguous access on that. Let's do it for a second. And see what that does. And here you see we improved the time by 4x and got to about 0.95 milliseconds. Just to show you what happens if we do it the other way around. Oh my goodness, even that is better. That is embarrassing. Wonder what it's choosing, but it's so bad. Anyway, so one other thing, but it was worse than what we had before. So one thing I can show you though is we said we have an iteration pattern here, right? And that iteration pattern should match what the matrix does. Right now the matrix is just defaulted, right? So everything is default. But let me change that and do a layout right here. Let's change back our tiling to what was the good tiling, the 64 times 4. You see, we are now at 9.4 milliseconds as opposed to 0.9. So we lost a 10x here on having the wrong data access pattern. But if we now actually put this in here, making it the matching iteration pattern, right? Kokkos iterate, right? And to also swap this guy around. We are back to the performance, about 0.9 milliseconds, which we had for the layout left case, as where the defaults were just matching, because the defaults are derived from the execution space. And so we are getting back to the same thing, right? The point here is that the iteration patterns have to, that allow you to control your access pattern as well. And so it allows you to match whatever your data structures are doing, right? But if your data structures are just defaulted and you just leave the defaults for the MD range policy here for the iteration pattern, they match up anyway already. So that's the way that works. Okay, let's go out of here. Let's go to the next exercise. So the next exercise was the Subview exercise. That's actually a pretty simple one. So what we want here is the whole exercise is essentially just to replace the in the dot product, right? Essentially get the subview first, and then do the dot product with the row view instead of the matrix view. So let's find that place. So we'll get the subview outside of the inner loop, because we want to make sure that that we amortize the creation of the subview. And essentially what we're going to do is we're going to get a row J. Use auto here, because who knows what we are getting. And now we get the subview. We give it first the thing we want the subview of. When we want the row J, so we give an index for the first thing, for the first argument, and we give Kokkos all for the second argument. And then what we can do now is we can use row J here, and it only takes a single element. While a lot of our examples started with one index as the first argument, it works the other way around. You can get like Kokkos all comma I. Yeah, that has nothing to do. There's no restrictions on that. Every place in a subview can take Kokkos all, a pair, or an index. Let's see if it works. And here we go. And that works. And we're getting 512 gigabytes a second. Let's see what we got before. What's the name of a output change? I think it's something in that neighborhood as well. 520, oh, also 512. Yeah, so it doesn't matter at all. So that subview doesn't cost you anything, but it means that, if you had a function, right, which were doing dot product instead of having written it on your own, sure, for dot product, it doesn't really matter because it's a simple, straightforward parallel reduce, right? But you can imagine that you have more complex things. So the point is that you could have used, the subview thing to make sure, to be able to call that other function which expects two vectors, right, instead of a matrix and a vector. So generally, subviews are a rather useful concept and widely used. Okay, so we had that. Let me think, what was the other exercise? We did subview, we did that, scatter view, right. So scatter view was the thing, which allows you to switch between these different scatter contribute patterns, essentially the using atomics versus using data duplication. And this exercise is actually, I'm actually pretty proud of that exercise, because I think we came up with a really good thing to show this. So what this exercise does is it actually calls in its main loop 3 different versions of the same algorithm. It calls a pure atomic loop. If you have OpenMP, it calls a pure OpenMP loop, which actually is implemented in raw OpenMP, which uses duplication, and the scatter view loop, which is essentially the one we now need to modify. So you see these three versions here. You have the scatter view loop. That's the one we need to update. Currently, it's essentially a copy of the atomic version. Then there is the atomic version, and you see the atomic version essentially just becomes atomic by making the memory traits of the result view atomic. And the way it works internally, right? You see it's using this indirection array here to essentially simulate this kind of random scatter access, right? And then the duplication one, that actually just creates a duplicated array. And you see that here it uses the OpenMP concurrency to essentially figure out, how many threads are alive, and then it fills it with zeros. Assumption here is that you would usually get this guy, you would reuse that guy, you would pre-allocate that instead of allocating it every single time you come to this kernel. And then it goes into the parallel 4, it figures out what is my thread, and then you writes into the result view of that duplicated thing, there. And then at the end it copies, it sums up over all the duplicates and writes it back into the actual result view. And so what we are now doing is we're changing this guy to use the scatter view. So first of all, we don't need the memory trait anymore for the incoming result place. So we'll take that away. Now we need a scatter view, and we create that outside the timer because, again, as I said, usually what we do is we keep them persistently around and leave them alive. This is still in experimental. We are probably going to release it as non-experimental not in the upcoming 3.2 we are preparing right now, but in the one afterwards. This is a general thing we do. We generally keep things a long time in experimental to essentially get feedback, but it also means that stuff which isn't in experimental is usually very, very, very stable. So I'll name that RS. And what we do is we create that from R. Now, usually if we came in here multiple times, what we would need to do is we need to reset potential duplicates, if there are any. So we'll do that. When we need to get the accessor in here, we'll use auto for that, and I'll call that RA equals rs.access. That either returns an atomic view of the data or the thread-specific duplicate. So now we're gonna increment into this guy, into RA. And then at the end of all of it, we need to contribute back. Contribute, and I think it's R, RS. It shouldn't compile if we get that wrong. Okay, that's it. So now what we can do is we can try compile this and see if it actually did include Kokkos scatter view. No, so scatter view is not part of Kokkos core, it's in Kokkos containers, which is a different directory with like more like data structures. So we need to explicitly include that. So let's do that. And let's start with a GPU build. So in the GPU build, the duplication loop will not be run. So what we expect now is that currently the thing is not set up to set the architecture to Volta. So let's change that. So what we should see now is that the atomic loop and the scatter view loop are the same performance, and that's what we see here, right? Where 8.5 milliseconds both. Okay, let's compile this whole thing for OpenMP now. And see what happens there. Let me just fix that. Export file. Okay, and what we see here is that, first of all, the atomic is significantly slower than the duplication. You see, that's like, what is that? That's 10. That's almost 30x or so slower. Largely, it is because essentially the atomic access here will do even, as the way I set this up, running across 2 sockets, right? You actually have atomic accesses across sockets. So you have really far away atomics, which makes it really slow. But the point is that the scatter view is as fast as duplicated. In this case, it was actually a bit faster for some reason. But oh yeah, because the first touch, the scatter view actually gets initiated so that the entire copy of the view is correctly first touched wherever the whole the core is, right, on the correct socket. While in the initial version, I might have not in the duplicated version, or the manually duplicated version, the first touch doesn't know exactly your access pattern, so it first touches in a way which isn't 100% optimal. The scatter view touches in a way which is 100% optimal. But just to show you what happened on P num threads, let's run something smaller, you know, just on the current socket. You see the difference here is getting smaller, right, between the scatter view and the duplicated. Okay, so that was that one, and then the last one is the dual view, and just go into that fast. So basically what the dual view is supposed to do is, it's the code, the way that it's set up, it runs essentially the sequence, like a time step loop, where you compute different physics properties, right? You compute pressure, you compute internal and stuff like that. And in the initial version, compute enthalpy is not ported. So what happens is that in the time loop where we control data access, we said, oh, we don't want to touch this guy at all. What we're gonna do is we're gonna get here the correct places, and we're gonna sync stuff back, right? So that's fine. The other loops themselves, they actually use functors here, the compute pressure and the compute internal, right? We use this, where is it? This functor here. And if you look at the functor constructors themselves have the sync and the modifier in it. So the functor knows I'm going to modify energy, so I'm going to mark it as modified. And the functor is templated on the execution space, so it can do that here locally, you know, also with just figuring out the correct memory space of what it's doing. So all of that works internally. So what we're going to do is we're just going to rewrite the enthalpy for a second. Where is that? What we're going to do is we're just going to pass on the actual data structures, so the dual views, which is like not energy view and stuff like that, but just the full things. Let's do that for a second. We need to make enthalpy also a dual view. It's the last data structure which wasn't. Okay. Let's delete this guy. Don't need that anymore. And what we're going to do is we'll just make this guy all view types. One could have a view type which has the const double instead of you know, just the non-const versions, but I don't think that we have that here. So we'll just replace that this way. Okay, copy that down. Oop. And now we're going to do something slightly different than in the functors. We know that we are going to execute this on the device. So what we're going to do is we're going to just get nfd equals. We're just going to get the views out explicitly. Dot. I think it's device. It's probably view device. So we get the 3 views here. I'm just going to do it for one now. I'm just not going to finish the whole thing because we are running a bit out of time. So you get the views here when you say, I want to, I'm going to mark this as sync device. I'm going to mark the energy as sync device because we're going to access it on the device. And then what you're also going to do is, because we modify enthalpy, you mark it as modify that, and then you just use these device views in here after switching those to parallel force. Okay, I think that kind of brings it across. Otherwise, there's the solution file. If you go to the solution dual view exercise CPP, you can find a whole solution for the entire thing. Let's see. Oh, this one actually wrote a whole functor. But yeah, if you have more questions on that, please let us know. Otherwise, we're gonna go on now. So, anything I should address?
No, you're good.
Okay, I'll go on. Hierarchical parallelism. So we're going to talk today about a few things. In particular, all are related largely to hierarchical parallelism. So the idea here is that you should learn how to leverage more parallelism through nested loops, not just parallelizing one loop. And we'll in particular want to learn about the concept of thread teams and vector length. We're also going to talk about scratch spaces. These scratch spaces allow you to get temporary workspace in kernels, and they also allow you to leverage things like the GPU shared memory. And last but not least, we're going to talk about unique token, and that allows you to allows you to acquire safely per thread resources in a portable way. But we'll start with hierarchical parallelism. So hierarchical parallelism is all about finding and exploiting more parallelism in your computations. And what we want to teach you here is how the outer and inner levels of parallelism are similar and where they differ. We're going to talk a lot about the concept of thread teams and the league of teams of threads and what that means and how it works. And we'll talk a bit about how these thread teams can help you improve performance, if you have these well-coordinated teams. Okay. Remember we had this exercise, right? That was this exercise we've been coming back, and this example we've been coming back again and again. We have this matrix A, we multiply it by a vector X, and then we'll multiply the result also by a vector Y, and we do that all in one kernel and get a single scalar value as a result. And what we did so far is we parallelized over the number of rows, right? Without a thing here. And that worked, reasonably well. We got pretty good performance when we had enough rows, but enough rows was, a dicey matter, because you needed actually 100,000 rows or something like that in order to saturate a GPU like a Volta. So what if you don't have that many, right? What if your matrix is not 100,000 times 1,000, but 1,000 times 100,000 or 1,000 times 10,000? Where do you get enough parallelism from? And there's a couple of solutions. One solution is we can use atomics. Another solution is actually we could actually write this as a multidimensional range policy. And then there's thread teams. Let's talk about the atomic kernel. So the atomic kernel would be something like that, right? Instead of just looping over the rows, you loop over all the elements and atomic add everything back, right? You get from your kind of collapsed index, back the row and the column index, which really is just a diff mod operation. And then you do an atomic add. There's a couple of problems with that. Essentially, performance will be pretty bad. And the reason that performance will be pretty bad is multifold. The main reason is that you're doing an atomic here and everybody hits the same value, but you also access Y again and again and again, right? Even though in the original code we wouldn't, right? We would only access it outside of the inner loop. So, but the main problem is really that using this atomic with every element is essentially doing scalar integration with atomics. And that's what we discussed in the last module, last week. But if you do that, you lose somewhere between 100 to 100,000x compared to doing, for example, a reduction. Now, one thing you could envision this kernel to look like when we, before we started parallelizing anything, what you really had there is you had, for each row, we did a reduction. We do a reduction. We do a dot product for every single row, right? And so you could have written it as a for loop over rows and then a parallel reduction on the innermost loop. And what this is an example of hierarchical work, right? For every something, you do some kind of parallel operation. This is an example of hierarchical parallel work, of hierarchical parallelism. And that's an important concept. So algorithms that exhibit this kind of hierarchical structure, those are the algorithms where you can exploit hierarchical parallelisms with thread teams. So what is a thread team? A thread team is a collection of threads which are guaranteed to be executing concurrently and can synchronize. What does that mean? So far, I always told you that our parallel loops do not guarantee how many execution agents are working at the same time. And we also do not give you any way to synchronize. There is no equivalent of things like a pragma OMP barrier inside of our parallel loops. There's very good reasons for that not to exist. One reason being it's not implementable on GPUs, or at least on certain GPUs. But thread teams are different. In thread teams, we guarantee you that a certain set of threads is concurrently working and that this subset of threads can synchronize. So the high-level strategy of how you use thread teams is that you essentially do one parallel launch of n teams. Then each team will handle a row. The threads within each team perform then a reduction, and then the teams themselves will perform a reduction for this kernel. And we will walk through this in detail, but let me just start with, where we want to end up with. So where we want to end up with is essentially this. We do this parallel reduction. We use a different policy type here, which launches with team, with hierarchical parallelism. When our lambda doesn't get any more an index, it gets this handle to a team to figure out, who am I? And then we do a nested reduction with yet another policy, which does the dot product. Okay. So where do we start? The first important point is that using teams is changing your execution policy. Similar to how we changed, to a multidimensional range policy from the simple range policy, the same happens with hierarchical parallelism. So instead of getting a range policy where you just give it the total amount of work or a begin and an end, what we do is we now use a team policy. And the team policy takes two arguments. It takes a team size and a number of teams. So you are telling it, I'm going to launch a certain number of teams, and that is independent of the hardware. It's essentially just the work set count. And you tell it the team size, and that is how many threads are associated or assigned to each of the work items. Okay. If you do that, your functor or your lambda, the operator, receives now a team member. It doesn't receive an index, it receives that handle. And that handle essentially lets you figure out, who is that team, who is the thread within that team and stuff like that. So you can ask it for how many teams are there, which is the league size. You can ask it for which team am I in that, the league rank. That's effectively your work set index. You can ask it how many threads are in my team. You can ask it, who am I within that team? And you can make the threads in that team wait on each other via a team barrier. One important thing to note here is, while we give you a team barrier, the semantics of teams are such that you couldn't actually legally write your own team barrier. It would be a legal implementation of Kokkos teams to have a compiler which essentially executes a team even with a team size of like 8 on a single thread. And it would essentially time slice it and said, okay, I execute the first thread until I hit a barrier. Then I execute the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth. And only after the eighth reached the barrier, I'm gonna come back to the first thread or the first state and continue executing that. Okay, that would be a legal implementation of this. So you are still not allowed to write your own synchronization mechanisms, but we give you some. So let's do a first attempt at that exercise, right? One thing we can do with that is, if we have this league rank and team rank, is we could start this, and just say, oh, you know what, I'm gonna launch a team of, I launch n teams of m threads. And then I can use directly the league rank and team rank as my row and my column index. Now, that doesn't really work if your team size is not the number of columns. In particular, if you have too many columns, you can't actually make your team size large enough. Like on OpenMP, the team size is limited to the number of threads in the OpenMP thread pool. On GPUs, the team size is limited, for example, by the maximum CUDA block size, which is 1024. The other problem is, if you did that, your data access pattern might actually be bad. So we see that in the second attempt at the exercise. So what we could do is we could just, instead of having exactly the same amount, the team size being the row length, we can just divide the row, the loop over the row among the team members, right? So we'll begin, team rank, and then we'll increment by team size, and we go up to smaller than m. The problem with that is it's still bad, because the atomic add is still there. So we need to figure out how to fix that. And the other problem is that the data access pattern is bad. What I actually implemented here is a data access pattern which gives you coalescing, but not caching. So this would, from a data access pattern perspective, perform well on a GPU, but would perform bad on a CPU. And the point is, we shouldn't really be hard coding the work mapping. You didn't do that with our parallel fours. So you shouldn't do that for kind of nested work either. And if you think about it, right, what we are doing there is we do a reduction over m columns with the team. And if you weren't already inside of a parallel loop, you just would use a parallel reduce with a range policy. But the point is, this is still parallel execution. And the teams give you the way of writing these nested parallel patterns. And that is where team thread range comes in. Team thread range is an execution policy for nested parallel patterns. It takes the team member. Essentially, it needs that handle to figure out, who is each thread and stuff like that, and then decide how to split this off. It takes a begin and end or just a count, like the range, like what you did for the normal parallel 4. And then you just have the same syntax as with the parallel reduce you already know. Right? You have parallel reduce, you get the policy, you get a lambda. In the lambda, it's the same as with normal range policy. You get an index, and for the reduction, you get the thread local variable. You sum then into that thread local variable, and you get something back. The same as with our normal range policy, the mapping of work indices to threads here is architecture dependent. That is essentially fixing our problem, what we had when we wrote this manual loop, that I wrote a coalescing loop, but that would be bad on the CPU. This thing does that again, right? It does coalescing, so it does like strided work assignments on GPUs, and it does chunked work assignment on CPUs. This M here doesn't need to be a multiple of a team size. The same as you didn't worry in a parallel 4 with a range policy or a parallel reduce with a range policy about whether your loop count, goes evenly on the number of threads in the thread pool underneath. You don't need to worry about it here. And then the intra-team reduction, as a reduction across the threads, is again done by Kokkos, right? You write the same as in the normal reduction. You write your reduction into the thread local variable, and then Kokkos will do the reduction at the end. Every thread here gets back the full result, right? That's why you can reduce into a thread local variable here. We essentially do a broadcast at the end. That's different from OpenMP, where you would actually need to have some way of declaring a shared variable here. In Kokkos, you don't need to do that. One note, this guy here, the nested loops do not use Kokkos lambda. The reason is that in CUDA, you are actually not allowed to mark them up as host device. And the compiler already knows which scope you're in and can figure out, what to do about it. So if we now look at the anatomy of, how this nested parallelism works, basically you have an outer loop, and that can be a parallel 4 or parallel reduce. You give it the label, you use the team policy, you tell it the number of teams and team size. And then you have inner loops, which use the team thread range. And those can also be, again, parallel 4 or parallel reduce. Note that I set explicitly loops. So you can have many of these loops one after another. Okay? You can have here parallel 4 followed by another parallel reduce, followed by another parallel 4, and so on. You cannot nest team thread ranges in each other. That would actually lead to some iterations not being executed. Okay. One last thing, the code is only valid Kokkos code if it works with capturing by value. Again, what we're gonna do is we make the lambda const. So you're not allowed to just modify external variables. There's good reasons for that. But in some situations, capturing by reference is actually better performance-wise. And it is legal to do that as long as you do not, as long as it also compiles with the equal sign. If you use our Kokkos Clang fork, kind of clang tidy roles we have in there, you can actually even if you use a capture by reference here, we will catch it if you do something with capture by reference which is illegal. So that could potentially help. Now there is a problem, and the problem is that you do not necessarily know, what is a good team size. And in practice, what you can do is you can let Kokkos decide what their team size is. What we have there is we have a heuristic which essentially just tries to figure out what is typical good values for that. And it takes into account, that there's special hardware available for coordination, that, for example, on NVIDIA, 32 threads or on an AMD 64 threads are executing in lockstep. It knows about maximum team sizes and stuff like that, and tries to do the right thing. On Xeon Phi, typically what we try to do is something like the number of hyperthreads per core. So that's for high hyperthread counts on architectures. On normal CPUs with just like 2 hyperthreads, it actually turns out that a team size of 1 is almost always the best. You do have a little bit of fighting over the cache on the core, but that is less bad than the extra kind of synchronization you need when you go from a team size of 1 to a team size of 2. Where is an exercise for this? In that exercise, you're gonna replace the range policy with a team policy, and then essentially make the inner loop of our exercise with team thread range. What you then can do is you can combine, experiment a bit with the layout and the spaces and the N, and see how does that perform in particular compared to exercise 4. One particular question is, how should A be laid out in memory? Okay, I'm seeing there a question whether team thread range uses dynamic parallelism with CUDA, and the answer is no. Think about the fact that I can tell you what my rank is, my team rank is, outside of the parallel for loops, right, or of the nested loops. That means all the threads are active all the time, right? A team in Kokkos, when you compile for CUDA, is a CUDA block, and all the threads are active at the entire time. What the nested parallel for loops do is they split the range over the already running teams. Effectively, it's the equivalent of a pragma OMP4 inside of a pragma OMP parallel. Indeed, it is a pragma OMP4 no wait. So threads can enter a parallel 4 and exit it while others are still in there or didn't even reach it yet, right? A thread will essentially just figure out what is my sub-range of that parallel 4, of that parallel loop, execute it, and then continue on. Okay, so if we look at this, look back at the exercise 4, right, which was essentially the thing where we played with the layout. We saw this thing, where on the GPU we needed layout left, on the CPU we needed layout right, and we needed almost 100,000 rows on a Pascal GPU to get full performance. Now, if you do this exercise, right, you will find something very, very different. First of all, on the GPU, you now suddenly also need layout right. Layout left is bad. But you also see that our onset of good performance moved 2 orders of magnitude to the left, right? Instead of 100,000 rows, I'm getting away with about 1,000 rows and get good performance. Here you see that. You see how the red moves to the left? So first of all, why do I need layout right? If you think about it, the tightly coupled threads of a team, we are now parallelizing the inner loop. And that means they want coalescing happening on the inner loop. In order for coalescing to happen on the inner loop, the rightmost index of the matrix needs to be stride 1, which means we need layout right. On the CPU, you don't have to change because you still want caching on the rightmost index. Another thing that changes is that we now lose performance on very high row counts. Very high row counts in this thing where I fixed the total size, the total number of elements, means that each row is very short. And so what you're doing here is we are now parallelizing the dot product, which is super, super short, with a team. And that team might actually have like 128 threads or so. So in fact, at this point, not every thread actually does any work. And on top of it, you do a parallel reduction now, which means you do like a reduction tree for all the 128 threads on the GPU. And that reduction tree costs you something, right? But for this whole entire reduction tree, you only do a couple of operations where every thread only plus equals, multiplies one matrix element with one vector element. So the cost of that is pretty high, and that's why you lose performance on this side. For very short inner loops, right, it's much better to do them in serial with a single thread instead of doing a reduction over a team. Now, if you were to play with the team size, you could move that a bit out, right? Because our heuristic doesn't know anything about what is your inner loop length. Not at the entry to the kernel, where I have to determine the team size. And that means it probably chose a team size which is too large for the very short row lengths back here in that regime. But the fundamental problem stays, right? That for very short row lengths, you can't fix this problem because the synchronization or the collaboration in the team, the coordination in the team is more costly than what you would gain. Okay, there's actually a third level of parallelism, and that's vector level parallelism. This vector level parallelism uses a thread vector range, and it can be used for parallel 4, parallel reduce, and parallel scan. What this does is it essentially maps the loops to, vectorizable loops to CPUs, and it decorates them with stuff like pragma IVDEP to give hints to the compiler, this is really vectorizable and you might want to try this. It also maps it on GPUs to effectively warp or sub-warp level parallelism, or wavefront or sub-wavefront parallelism. The vector length, or the desired vector length, is actually provided as a runtime argument to the team policy. What you do not have is you do not have explicit access to a vector lane ID. Okay, you can only use that implicitly through nested loops with a thread vector range. There is one problem though, and that problem is that depending on the backend, the entire team policy operator is executed redundantly by all active vector lanes. Where's that coming from? That's coming from CUDA, right? If I'm launching this with CUDA, what we effectively do is we map the vector lanes to the X dimension of a CUDA block and the threads to the Y dimension. But all of these CUDA SIMT threads, right, are active the entire time, which means every statement is redundantly executed outside of a SIMD loop by all of a thread vector range loop by all vector lanes. And we'll tell you how to fix that in a bit. Okay. On a CPU, the vectorization happens implicitly by the compiler, which means that statements outside of a thread vector range are not redundantly executed by all vector lanes. Okay. There's also team vector range available, and that uses both thread and vector parallelism. So how does that look like? Basically, you can write stuff like this. You can have like an outer loop, which is the team policy. Then you can start a team thread range. In that team thread range, you can do a thread vector range. You can also do at the same level as the team thread range, you can do a team vector range. You can actually do a thread vector range at the same level as a team thread range, right? Because you already have access to the thread ID itself. So that's legal. What you cannot do is you can't have a team vector range inside a team thread range. You can't have a team thread range inside another team thread range. And all of these guys here support like parallel force and parallel reduces, and the thread vector range also does the parallel scan. We are going to implement the parallel scan for team thread range and team vector range too. But for a long time, we didn't have any real use cases. You can have tons and tons of these nested loops. A customer at Los Alamos actually broke the GCC compiler at some time, which apparently has a hard upper limit of not more than 64 nested lambdas inside an outer lambda. So you can write really complex code with this. One thing, all of these guys take this team handle as an argument. So you can actually have all of these loops, sit in like separate functions and even separate classes and stuff like that. What you need to do is you need to pass the team handle on. And that design is very much by choice. Actually, we could, in principle, regenerate the team handle in many cases out of thin air. But we do not want to do that and support that, because passing the team handle on in your API, right, of like function calls and stuff like that, indicates, oh, this is a thing supposed to be called inside of a hierarchical parallelism team policy loop or team policy section. And it gives you a thing, which says, oh, and this function will probably use nested parallelism, right? So that's why we do that. Okay, so I said we have redundant execution, right? And I'm trying to make that a little bit clearer with an example here. And you probably need to think about that example a few times before you're gonna, or the example series here, a few times before you really, understand that in your hearts of hearts. But I promise at some point, you're gonna think, oh yeah, that's reasonably natural. So I have this loop here, this parallel reduction. And the question is, what will the value of total sum be? What I do in this parallel reduction is I kind of figured out, what's number of threads by basically asking for concurrency or something like that. Doesn't matter. And then for each iteration, I'm doing a sum, right? Effectively, every thread will get exactly one iteration. So every thread will effectively do that in a loop once. So first thing is, what will this thread sum be? Relatively straightforward, right? If we start from the inner point, you just do a loop over 10, it just plus increments it 10 times. So this thread sum will be 10. So every thread will contribute 10. That means we get number of threads times 10, right? The loop count here times 10. Let's replace it with a team policy and do here number of teams and team size. What do we get now? Let's start at the middle here. We do the sum again, and that means this thread sum turns out to be 10 again. Every thread in the team does that and contributes that back. So I'm getting team size times 10 for every team. And I have number of teams. That means I get number of teams times team size times 10. Now I do something additionally. I wrap this inner loop into an additional parallel reduction. But I make the parallel reduction only run team size iterations. That means every thread in the team will execute that inner thing here once. Okay? Every thread will do that once. So this increment will actually be executed exactly the same amount of times as in the previous example. But the answer changes. Why? I get this thread sum in here to be 10. It then contributes that to a reduction within the team. That means this team sum at the end will be team size times 10. Now, this statement out here is executed redundantly by every single thread, right? Every thread executes that still. Every thread is active outside of the parallel reduce. That means every thread in the team will contribute this team's sum back to the entire sum, to the global sum. So that means every team will actually contribute team size times 10. And that's why you get a team size square in here. Okay. The point is, the inner reduction already computed the team size, the whole value of the team. But then, because I don't protect this extra statement out here, I'm doing that with every team member again, right? Contributing that thing back. This value got broadcasted to every team member. Okay. How do I fix that? Because that's probably not what you wanted. You probably just wanted this guy to, contribute once, this team. And that's where the single pattern comes in. The single pattern is essentially used to restrict execution to a subset of threads. It's like other parallel patterns. It takes a policy, a lambda, and potentially an optional broadcast argument. And there's two policies. There's a team per team and a per thread policy. It's really equivalent to the OpenMP single directive, actually with a no weight on it. So in the simple case, what you can do is you can do single per thread or single per team. The lambda doesn't take any arguments and just executes the code with one guy. Why is there a per team and per thread? The per team just means, this will be executed once per team. The per thread means mask out the other potentially active vector lanes, right? On a CPU, the per thread thing actually doesn't do anything, right? It just executes the code without any conditions. On the GPU, it masks out everyone except for lane 0 of the X dimension of your CUDA block. There's also a version which broadcasts, and you use those in particular for things like when you do an atomic fetch add, for just once per team. And everybody needs to get the result of that atomic fetch add. Like you did a reduction, you computed the value which needs to be contributed atomically, and one guy contributes that and gives the previous value back, right? That's what this is for. And it works kind of like the reduction. You have where you want to have a final result stored in every thread, right? You do the single construct with a per team policy here, or also per thread, that works as well, if that's what you need. And then you do the signature of the lambda now takes, like the reduction argument, the thread local variable you need to modify. That's the thing you assign to and modify. And that value, whatever you wrote into this thing, right, is then broadcasted at the end of a single statement. There's an exercise for that, which adds, essentially it's like the previous exercise, just that it adds an additional elements loop around our y times ax. And what you need to do here is you need to essentially now parallelize the third loop level, okay? And you can use the single policy to restrict, the execution in places where it needs to be done. So there is a question on, everybody gets it, right? So I said in the single broadcast value, everybody gets the value back. That is different from just having member 0 do something in that if, you would still need to call the broadcast. Generally, thinking of this as, oh, member 0 does the per team, the single per team thing. It's as if I had a, if team rank equals 0, do this, is actually not far off from what actually happens. It actually is what happens in most of the time. In particular, if you do not have a third parallelism enabled. Okay, if we look at the result of this, right, and what it's compared here is the 2-level version of this, there's this 3-level loop with elements, and then for every element doing the y times ax. And in the begin section, in the begin version, it only parallelized 2 loops with a team policy and the team thread range. And what the thread vector range gains you is essentially some performance improvements, in some cases more, in some cases less. On the CPU, for the most part, it doesn't actually matter. It only really helps you for short row lengths, where the better explicit parallelization improves your performance. On the GPU, you gain somewhere around like 20–30% for the most part. And just in a couple of special, sweet spots, you gain like 2x. If you look at this point here, right, that improves about 2x. So generally think about this third level parallelism as something you really only do as a performance improvement, right? It's not something you necessarily start design from the beginning, okay? So to summarize, hierarchical work can be parallelized via hierarchical parallelism. In hierarchical parallelism, you leverage thread teams, which you launch via team policy. And when the team work sets are processed by a team, and you use nested parallel force or reduce or scan, for the thread vector range, with the team thread range, thread vector range, or team vector range as policy. And you can restrict execution in places where it's necessary with the single pattern, using either a per team or per thread policy. Okay. Any other questions we need to answer?
No, you continue, Christian.
Oh, Damien, can you say again? I had actually myself on my...
I said keep going.
Okay.
Nothing you need to stop for.
Okay, so next thing we're going to talk about is scratch memory. And what we do with scratch memory is we want you to understand, the concept of a team of thread private scratch pads, which you can use with team policy. We want you to understand how that can reduce global memory accesses and thus get you potentially better performance. We want you to understand when to use scratch memory and how to use it in the way, in particular, also how that makes barriers potentially necessary. So in Kokkos, there's 2 levels of scratch space. We have a level 0 and a level 1. The level 0 is pretty limited in size, but pretty fast. And the level 1 is larger, but the allocations are essentially equivalent to having like pre-allocated stuff in high bandwidth memory with the kind of latencies and bandwidth which comes with that. So think of the level 0 as kind of a manual L1 cache potentially, and level 1 just as your nearest kind of mass storage. You can have team or thread private memory. And if you use it as that, right, it's typically used for like per work item temporary storage. There is an advantage over pre-allocation, and that is essentially that the aggregate size of the scratch only scales with the number of active threads, not with the number of work items. And we'll come to that back in a bit. The second use case, primary use case for scratch space is manually managed cache. Essentially, you can cache manually things which you access frequently. And this is the only way of how you use, like this hardware-specific manual on-core scratch space, like, for example, NVIDIA's GPU shared memory, when I think this big Chinese machine had or has manual managed scratch, and that's what exposed with this through too. What we're going to discuss largely is the manual managed cache use case. So the examples we have are for that, but this, the way it works, the mechanics of it are exactly the same, right? It's using the same API, it's using the same mechanisms underneath. It's just, a different flavor of use case. So let's look at something like this. A contract data field, function. So that's something you have a lot in like finite element codes, right? You loop over elements, you loop over a number of quadrature points, and when you do something for each of these quadrature points. It actually looks pretty similar to what we did in our earlier exercise. But as said, often you do that per element, right? This actually looks like the exercise for the vector length we did, right? Where you do a team policy for the number of elements and then team thread range and vector loop. So we do something like that, right? And there's different ways of how to parallelize that, right? You can have each thread handle an element, right? That gives you number of elements total parallelism, which is potentially good. You can have each thread handle a quadrature point, which gives you more parallelism. Or you can have each thread handle an I, but that requires then reductions. So we don't want to do that. What we do is we do each thread handles quadrature points. And there's different ways of doing that. One way to do that is you can use an MD range policy, right? You just tell it, I go over the number of elements, the number of quadrature points, you get the element at quadrature point, and you do the loop internally to do the computation for each of these element quadrature point pairs. But one thing is we can also use a team. And we'll come to why we would want to use a team to do the same thing here in a second. Essentially, what you could do is you could just do the outer loop with a team, right? When you get a team member, you figure out your element by getting the leak rank, and when you do a parallel for with a team thread range. So there isn't really any big advantage yet. But one thing you might notice is that the access to BE element I is independent of QP. So every thread in this particular team will actually access the exact same vector of B. Okay? And that gives us an opportunity to improve potentially the performance of this kernel. How so? Essentially, we get that opportunity because each team actually has access to a sketchpad. It can coordinate. In some sense, this is similar to what might have happened back in primary school or in kindergarten or so. You have a group of kids who are sitting around the table, and we all are supposed to color. Now we could all walk, every time we need a color, to the shelf, get the pen, go back, color their thing, and then bring the pen back. But that has a lot of, movement going on. Everybody is going to global memory, everybody is waiting at the shelf, on each other to, reach in. And you don't really want that. So instead of doing that, what you do is you go once to the shelf and you get a stack of pens, put it in the middle on your table, and now everybody can just reach with their arms in the middle of the table, get the pen they need, use it, and then put it back in the middle of the table, right? That reduces contention on the shelf, and it makes the access significantly faster, right? And that's what we can do too. Each team has shared memory or sketchpad available to itself. And what you can do with that is you can load things from global memory into that shared memory, then collaboratively work on that, and then maybe put it back. So if you use that sketch memory as a manual cache, one of the reasons why you might want to do that is because accessing data in that sketch memory is usually much faster than in global memory. In particular, if it's in level 0. GPUs have a separated, dedicated scratch memory. And we actually have scratch memory which is only accessible through manually caching, the shared memory. And while CPUs don't have this kind of special hardware, we only have the normal kind of L1 cache in the course. If you write your algorithms that way, with this explicit caching, with the scratch pads, right? What you're effectively doing is you're writing cache-aware algorithms. You're writing cache blocking algorithms. So you actually end up writing algorithms which are better, potentially, for your architecture and which are easier for for the hardware to figure out, what cache lines do I actually need to keep around. Basically, it's like a user-managed L1 cache with manual scratchpad. So the point here is, when members of a team read the same data multiple times, it can be better to load that data into scratch memory and read it from there. I earlier mentioned that we have this other scenario, right, the per work item storage. And that's a slightly different motivation for using scratchpads. Essentially, you do that when your algorithm requires some temporary workspace of some size. Say you need a matrix and you compute the matrix in that team, you use it, and afterwards you don't need that matrix anymore, right? In some serial CPU code, what you might have done is you might just have created a C array, and using like C++ extensions in GCC for variable length arrays, to just create it on the fly. You can't do that in Kokkos. We do not allow you to allocate data. Also, it might be slow. GPUs don't really allow you to allocate data on the GPU. There are ways, but they are complicated and they have all kinds of drawbacks. So we just don't allow you to do that. What you could do without the scratch memory is you could pre-allocate your matrices for every work item, right? You could just pre-allocate n of these guys. But that might be a lot of storage. You actually don't need that, right? What you need is you need one for every team, or maybe every thread. So you need t times w instead of n times w. And if t is significantly smaller than n, right, then that would be significantly less memory. I said you can do that, you might need that per team or per thread. And we actually support that. So we support scratch memory per thread or per team. And you can also have both, right? You can actually have allocations which are per team and per thread at the same time. You can use level 0 and level 1 at the same time too. But the point here is, if an algorithm requires temporary workspace for each work item, it is almost always better to use Kokkos scratch memory for that than other solutions. That's actually not true for caching. Sometimes the hardware caching actually does a perfect job and you don't need the manual caching strategy. But if you need temporary work storage, then scratch memory is almost always the best way to go. In either case, how do you use that? So what you need to do is you need to tell Kokkos how much scratch memory you will need. And you need to do that, at the kernel launch point. Then you create scratch memory views inside your kernels. So how does that work? You have a team policy, you create the team policy here. You have a scratchpad view, and we use a special memory space for that. We essentially use the scratch memory space of the execution space. Okay. Each of these views actually has a static function on it called shmem-size. And what that returns is how many bytes would you need to create a scratch view of that type. And what the argument here is essentially just all the runtime length arguments, which you would also give to a constructor. One reason why you need that is you potentially need more scratch memory than you think because you need to align the stuff correct. And I'll come to that in just a second. Then you tell the policy, what is my scratch size? You tell it which level and whether you want the bytes on a per team basis or per thread basis. When you launch it, and now the team member gives you access to that scratch space. And the way you create the view is, it's kind of like the unmanaged views. You give as a first argument this team member.team scratch or thread scratch and the level. Okay? That level better match, whatever level you used here. Otherwise, you're going to get a failure with not enough, scratch memory available. And then just the runtime dimension. So why this shmem-size thing? If you created multiple of these guys, right, you could just have size t bytes equals scratchpad view, shmem-size times vector size or vector size plus, scratchpad view colon shmem-size 3 times vector size or something like that. And you can have different scratchpad views, one with doubles and one with ints. Say you have one with ints and one with doubles, and you create both of those here. And you create the int one first. If that guy has an odd number of elements, right, your scratchpad pointer internally will be advanced to a thing which is 4-byte aligned. If you now would just create the double scratch view here from that, your alignment is off. So what this thing does different than the unmanaged view constructor, it takes the current state of where the scratch pointer is, and then it resolves the alignment issues. And that's why you need potentially a few more bytes so that I have space to resolve the alignment issues. And that's what this shmem size function takes into account. Okay. So how does that kernel now look like? We'll start at our thing and then we create a scratch. And the reason that we create that scratch is, as I said earlier, this access, the B access, is independent of quadrature point. Every thread in the team accesses the exact same vector of B. So what we want to do is we want to store that vector in scratch space. Okay. So we create that guy, we create it of vector size. That was the loop count here. That's the count over I, right? What we still need to do is we need to load that slice of B into the scratch. But then within the parallel for with a team thread range, instead of accessing B element I, we now access just scratch I. Okay. So how do we load this thing? You could have one thread load all, right? If team member team rank equals 0, do that loop. You could do it with a single statement as well, right? This would be similar to a single, per team statement, and that would work. But it's serial, so you don't want to do that. You could try and, each thread loads one entry, B element team rank, but that doesn't really work, if the team says it's not the vector size. So what you do is you do another loop and you use the team vector range because it's at the first nesting level and there's not any nesting happening inside. So we use a team vector range. We use all the parallelism available. We loop over vector size and assign the elements. Great. Now, there's still one thing missing here. One thing I said earlier is that all our loops are essentially no-wait loops, right? That means one thread might be done with its part of writing the scratch memory and start going in here, but it will loop over the entire array. And so it might access elements which aren't actually written to yet. So what we need to do is we need to wait here to make sure that all the elements are written before we go on. And that's what the team barrier is for. There was a question in the chat whether scratchpad views can be multidimensional. Yes, they can be multidimensional. There's no restrictions on the scratchpad views compared to normal views, right? They are just effectively unmanaged views, with a special memory space. We have the layouts, we have all the other things. We even have like memory traits like atomic access and stuff like that. One thing which is different with our scratch views is, because we are unmanaged, right, you can't deallocate them. There's also no way to turn essentially the scratchpad pointer back, right? You can't free a scratch array and get a new scratch array instead. If we wanted that, we would need to write essentially a full kind of memory management and garbage collection and stuff like that system. And we don't have that, and we don't want that. What this does is really just, it takes the current state of the pointer and advances it by whatever the shmem size is of the view we just allocate. As a consequence, you also need to call the creation of scratch views with every thread of your team. It is a collective operation. If you do not do that as collective operations, the threads don't agree anymore where the scratchpad pointer points to right now. And so if we create later a new scratchpad view, it will actually be different memory and different threads. And that would be bad. Okay. So there's an exercise for that. And essentially what that does is it takes the previous thing, the 3-level vector loop thingy, and just adds, that you cache the X vector. If you do that, you get something like this. First of all, we see that on CPUs and on Kernel, largely it doesn't change anything. The reason that it doesn't change anything is that the standard hardware caching just does a good enough job, right? It doesn't help you to do manual caching here. In fact, on this very left side, you see that performance actually drops for Kernel, right? For the version with the scratch memory. The reason is that you don't have any reuse, right? The number of rows is really small here, and that means your reuse of your X vector is really small. And so essentially what you're doing is you're copying something from global memory into another array, and then you read it from that array once or twice. And that extra read, right, that extra read-write thing essentially just costs you performance. If we look at the GPU, and what we used here is level 0 cache, we see there is a regime where we gain quite a bit of performance. This graph stops here because at this point, my vector length was too large to fit into this manual cache. What you see here, this bump, is where the L1 cache kicks in. So you have the same effect as on CPUs. The extra manual caching doesn't really help you because the L1 cache is already covering this. So when we look at this a bit more detail, about what you can do, you can allocate scratch in different levels. That's what we said earlier, right? There is this level parameter on the set scratch size, and it can be level 1 or level 0. You can use per team or per thread storage, or you can use both at the same time. You can tell per team and per thread and level. You can also provide set scratch sizes for both levels, right? You could actually do, set scratch size 0 per team, per thread, and set scratch size 1 per team, per thread. That works. Oh, this statement is not correct anymore. Set scratch size modifies the existing policy at this point. So what did we learn in this section? We learned that we can use scratch memory with team policy, and it provides either thread or team private memory. There's 2 use cases for it. There's the per work item temporary storage use case and the manual caching use case. It does expose the on-chip user-managed caches, for example, on NVIDIA GPUs and AMD GPUs. You need to determine the size before launching a kernel. And there's 2 levels available. Large but a bit slower memory, and small and fast. Okay. With that, we come to our last topic for today, and that's unique token. We'll try to teach you, what is the concept of unique token and how it allows you to get thread-safe resource access. Show you how this gives you per team unique IDs. And we'll talk a bit about the difference between a global and an instance scope for the unique token. So why do we need a unique token concept? Where's this coming from? Essentially, if you think about it, inside of your functor operator or lambda, there's not really a portable way to identify what you are executing on. There's no real way of get like a hardware thread ID, right? In particular, not in the range policy. In the team policy, you can at least identify who you are within the team, but you cannot actually identify which hardware threads you're on, because that depends on which team you are and how the teams were mapped to hardware resources. But there are algorithms where being able to identify exactly which hardware thread you are is actually useful. For example, you can get back access to like some pre-allocated resources which are cache local, right? And stay cache local over iterations. The problem with that is that while that is useful, there is actually no portable or way across all these execution environments to do that. And I'll show you that in a second. And that's where unique token comes in to provide that unique identifier. One of the first real use cases we had for that, why we invented the whole thing, was something like this. So we had this, we needed random numbers inside of loops, right? And you can't really share random number generators across multiple threads, very efficiently. There's a lot of, it would involve a lot of atomics. So what we wanted is we wanted a random number generator pool, and that every thread would essentially use one of these generators as long as it needs it, and get good random numbers. Now the problem with that is you need to figure out how many generators do I actually need? How many random number generators do I actually need? This K. And then you need to figure out, oh, which random number generator am I supposed to use inside my loop, right? And it's actually easy in OpenMP. If you were in OpenMP, right, you could just get OMP get max threads, that's great. And then you use OMP get thread num to figure out which one to use. That's easy. In CUDA, it is not really easy. Effectively, sure, you could compute something like this, right? Thread IDXX plus blockDimX plus block IDXX or whatever. The problem is that actually is just I. So your pool would essentially consist of a generator for every iteration. And that's not what you really want. Right? First of all, it would take a lot of memory. And second, it actually doesn't give you as good random numbers in general, right? Because you start with a new generator for every iteration. So you don't really want that. Yeah, come on. And that is where the problem comes from, right? In CUDA, there is actually no way to get your hardware thread ID. You cannot do that. And that's where unique token comes in. That is supposed to give you a thread-safe and portable way to obtain a unique identifier, which is effectively thread-specific. So what is unique token? Unique token is effectively a pool of IDs. And what you do as the user is you acquire an ID and then you release it again. And you see that here. You create that object, unique token. You can ask it, how many different IDs are there? And then within your loop, you acquire a token or an ID, and then you release it again. Okay. A couple of rules. You should not acquire more than one token in an iteration. You should not call acquire more than once inside of that thing. The reason is that might actually lead to deadlocks. The same as if you do not release that ID again. If there are only as many IDs available as there are threads, right? If you try to get that thing multiple times, what happens is it essentially looks in the log table and logs multiple guys potentially. And then other threads do not have any place to go and they just loop forever. So by default, that's why by default, the range of IDs you get back is something like 0 to execution space concurrency. Okay. Now, sometimes you need actually a global unique token. That means you need unique identifiers which are conflict-free across different kernels which might run concurrently. One situation where you get into that is if you submit concurrent kernels to CUDA streams. That's something we're going to discuss next week. Another situation is if you use Kokkos inside a multi-threaded environment like Legion or Uinta or something like that, and have multiple threads submitting kernels at the same time. And if you are in that situation, unique token can still help you because unique token is scoped. It has a scope template parameter, which by default is instance. That means the IDs are specific and conflict-free just for that particular instance of unique token. But there's also a global version, which effectively gives you back a singleton. And what you can do with that is you can have these two different functions, right? You create this unique token with the global instance. And then when you use these tokens inside your functor A and functor B, and these guys execute at the same time because we were submitted to two different streams. Don't take that too literal here, please. This is not a CUDA stream. We'll talk about that next week. But if you do that, then IDs obtained inside these two kernels will be conflict-free. Okay. Another situation is when you need a unique ID on a per team basis. Generally, right, there are less teams active when there's total threads, right? So you do not want the unique token for like the general concurrency, right? You want something which has a smaller range of counts. And the question is, how do you get that ID? And that is where unique token allows you to size itself. So essentially, unique token supports custom ranges, at least for its instance version, via constructing size tokens. And if you do that, it essentially requires 3 steps. So first, you compute the range you need, essentially using concurrency and team size. I'll show you that in a second. Then you create that sized unique token, and usually for performance reason, you make it a little bit larger than necessary. I'll talk about that in a second too. And then you acquire and broadcast the ID from the token in using a single pattern. Let's look at that code for a second. So you start with figuring out what is the team size you want, right? And that might be something like 128 or so, or 256 on a GPU. That means the number of actually simultaneously active teams is significantly lower than concurrency. You just compute that by the execution space concurrency divided by the team size. And now that means you can create a size token. And usually what we do is we do it, maybe 10%, 20% larger. The reason that we do that is in the acquire, on certain hardware, right? Not on OpenMP. On OpenMP, we can just return essentially the OMP thread ID, right? Doesn't really matter. But on GPUs, we go through a log table. And so if you make the log table exactly as many entries, as you have requests, right? It can potentially take a long time to find an open spot for somebody who tries to acquire something. If you make it a bit larger, right? You have more gaps in there and you have a much faster find, right? So then in the kernel, you use that single pattern, and you use a single pattern with a broadcast, right? So one guy of the team will acquire the ID and then broadcast it to everybody. And after you are done using it all, you release it again in a single pattern. There's an exercise for that. We like our exercises. It's actually a pretty simple exercise, but it kind of uses the scatter add loop from before. Just that we now use duplication always, and we use unique token to figure out what is the duplicated version we want. It actually is almost exactly what ScatterView does internally. Okay. So as a summary for unique token provides you a thread safe and portable way to divvy up thread or team specific resources. You can have a sized version so that it only returns IDs within a specific range. Note, it's really important in that case that you do not try to acquire more IDs than simultaneously when the range can give you. again, if you do, you potentially can deadlock, at least on GPUs. There's also a global scope unique token, which gives you safe IDs across disjoint code sections which run concurrently. Okay, with that, we actually reached the end of our today's lecture. What we covered today was hierarchical parallelism, and we discussed there how you can parallelize hierarchical work with hierarchical parallelism. We talked about how it leverages thread teams, which are launched by a team policy, and then how you can use for each of these work sets nested loops, nested parallel fors or reduces, or in some cases scans with a team thread range or thread vector range and team vector range. You can restrict execution inside of these teams via a single pattern using a per team or per thread policy. And that is necessary because you have a lot of redundant execution going on. And you can use teams to reduce contention for global resources. We talked about scratch space, how scratch space can be used with a team policy to provide thread or team private memory. We discussed the two use cases for that, the per work item temporary storage and the manual caching. We showed you that scratch memory can expose on-chip user-managed caches, like on NVIDIA GPUs and AMD GPUs. You need to determine the size before you launch the kernel, and there's two levels available. There's a large and slow and a small and fast level available. One thing about the large one is you can actually use that to allocate like megabytes per team, right? That's something you are actually allowed to do, and we have people doing that. Last but not least, we talked about unique token and how it gives you a thread and safe portable way to divide thread-specific resources, and that you can. We talked about how you can make a sized one, which restricts the range of IDs you get back from the unique token, and how there's a global unique token, which you can use in situations where you have multiple kernels running concurrently. Next week is going to be interesting because we're going to talk about tasking, in particular about fine-grained tasking in Kokkos. And we're going to discuss how you express essentially dynamic dependency structures for tasks. So this allows you to build dynamic task graphs on the fly on the GPU. Okay. We're going to talk about streams, essentially how you have like concurrent execution spaces, and how you use also things like CUDA streams with Kokkos execution spaces. And we're going to talk about SIMD types. We're going to talk about explicit vectorization via vector types and how that helps you improve vectorizations and how it's an alternative to thread vector loops. In particular, how SIMD vectorization allows you to effectively outer loop vectorization. Don't forget, join our Slack channel, drop in, ask us questions. We're also going to launch up a Zoom session on Tuesday afternoon again for people who want to drop in and ask random questions. Feel free to come. So far, I think we didn't have many people show up, largely one person. So, you can monopolize a lot of Kokkos Team time if you actually show up. We recently set up kokkos.link, and you find the recording slides at kokkos.link/lectures and updates on things, including also the login for the Tuesday session. We'll post that usually shortly before the session and the lecture updates. And with that, I hope to see you all next week again. Thanks for joining us today, and happy Kokkos coding.